For chapter 6, we'll start discussing uniform circular motion and gravitation. We've been discussing just linear motion up until this point. Now we'll begin going in a circular path and discussing the pretty much the formulas we've talked about up until now and how they can go into a circular path. From there, we'll jump into gravitation, and obviously we'll talk about force of gravity, but how some of the laws that we've already known can interpret into a larger scale, such as space and stuff like that. But first, we will define uniform circular motion as the motion in a circular path of a constant radius and constant speed. An example would be a ball on the end of a string of fixed length that always has the same number of rotations per minute. Notice that we specify constant speed and not velocity. Uh, why do you think this is? Remember that speed is a scalar and velocity is a vector. Well, because the direction changes and the velocity is always changing as the object moves in a circle. So because of that, we have to bring in some circular path formulas so we can also talk about our velocity in a different sense. For this figure, we have a CD. All points on a CD travel in circular arcs. The pits along the line from the center of the edge all move through the same angle delta theta in a delta t time. Obviously, if we start from point 8 here, you have to go to point B. You are going to be changing your angle that you're going in, and it's going to take you a certain time to get there. So that means we're also talking about our radius. If we're going all the way to the outer edge, we have to talk about the radius. The radius of a circle is rotated through an angle delta theta. The arc length delta s is described on the circumference. This means we can define the angle of rotation to be the ratio of the arc length to the radius of curvature. So we have our first equation here. Delta theta equals delta s over r. The arc length, delta s, is the distance traveled along a circular path, and r is the radius of curvature of the circular path. For one complete revolution of a circle, the arc length is equal to the circumference of the circle. This means that delta theta is equal to 2 pi r over r. The 2 pi r we get because that's the equation for circumference of a circle, and the r is just coming from the equation we just talked about here. So if you cancel out both r's, because you're going in a complete rotation, you get 2 pi, which is also 360 degrees, and that gives you the full rotation of the circle. We can use this result to define the units we will use in a circular motion. Delta theta is a measure in radians, and radians are defined so that there are 2 pi radians in one revolution of a circle. So we have our degrees in radians here. We have 30 degrees equals pi over 6. 60 is equal to pi over 3, and so on and so forth. That's a little trigonometry we have to bring into here. So that brings us to angular velocity. So how fast is the object actually spinning? We would define this as an angular velocity, omega, by that w. Typically, this is expressed as the amount of angular rotation, delta theta, per unit delta t. So omega is equal to delta theta over delta t. That look a little familiar? This is pretty much saying, okay, we're going to go a distance over a time, which is pretty similar to our velocity, is equal to delta x over t. So we have angular velocity, which is omega, is analogous to linear velocity, v. In fact, we can compare these by taking the angular velocity and calculating how much arc length is covered by that angle. So if we're talking about arc length, we have to bring in our delta s, as we do here. So our v is equal to delta s over delta t. And since delta theta is equal to delta s over r, we're going to substitute that delta s there. So we get v is equal to r delta theta over delta t. But since we know that delta theta over delta t here is equal to omega, which is our angular velocity, we end up with our radius times our omega. So the linear velocity is just the angular velocity times the radius of the curvature, which, think about it, it makes a little sense. You still have to take into account the velocity that is going on, but you have to include the radius as well. For points 1 and 2, they rotate through the same angle, delta theta, but point 2 moves through a greater arc length, delta s, because it is at a greater distance from the center of the rotation. In this example, both points have the same angular velocity because the cover of the same angle per unit time, but point 2 has a greater velocity v since it covers a more distance per unit time. So this radius really comes into an effect here. They have the same angular velocity, but it takes them a little bit longer to get there. So that brings us to our first example. We have a car moving at a velocity v to the right, has a tire rotating with an angular velocity omega. Okay, so we have both velocities here. The speed of the tread of the tire relative to the axle is v, and the same as if the car were jacked up. Thus, the car moves forward at a linear velocity v equals r omega, where r is the tire radius. A larger angular velocity for the tire means a greater velocity for the car. Show this by calculating the angular velocity of a 0.3 meters radius car tire when the car travels at 15 meters per second. So I will say this, most of this problem here is all fluff, extra. You really only have to worry about, you have an angular velocity, a linear velocity, we have a radius, and we have a velocity. So that's how we get our information from there. And it's a little easier to interpret some of these problems just by taking away all the extra wording and really just absorbing what the information really is. So since we have a velocity, linear velocity, I should say, of 15 meters per second, and we have the radius, we really just have to plug into this equation here. So we have 15 meters per second over 0.3 meters, and that gives us 50 radians per second. We have to say radians because we are talking about an angular velocity in a circular path. So this one's pretty straightforward. Right, so for this figure, as an object moves in a circle, here a fly on the edge of an old-fashioned vinyl record, its instantaneous velocity is always tangent to the circle. The direction of the angular velocity is clockwise in this case. So all this is saying is that even though the fly is here at this moment, yes, it's still going on a circular path, but the linear velocity here is always tangent here to this surface. So here it's going to go straight to the right. Here it's moving downward because our velocity is tangent to the surface. If it was down here, it would be going to the left. I mean, even if it was in the middle here, it'd be going tangent at a 90-degree angle versus the surface here. So that brings us to centripetal acceleration. Remember that we define uniform circular motion as the motion in a circular path of constant radius and constant speed. We know from kinematics that acceleration is a change in velocity, either in its magnitude or in its direction or both. In uniform circular motion, the direction of the velocity changes constantly. So there is always an associated acceleration, even though the magnitude of the velocity, which is the speed, must be constant. You experience this acceleration yourself when you turn a corner in your car. If you hold the wheel steady during a turn and move at a constant speed, you are in a uniform circular motion. What you notice is a sideways acceleration because you and the car are changing direction. The sharper the curve and the greater the speed, the more noticeable this acceleration will become. But what is the magnitude and in what direction is this acceleration? So here the directions of the velocity of an object at two different points are shown, and the change in velocity v is seen to point directly towards the center of the curvature. So here, because AC is equal to delta v over delta t, which is just our centripetal acceleration here, same acceleration we've been talking about. Centripetal means towards the center. So our acceleration direction is always going to be towards the center of the circle. So the acceleration due to uniform circular motion, centripetal acceleration, always points towards the center of the circle. But what about the magnitude? We're talking about angular velocity and a delta angle, delta theta. So here we have to incorporate that as well. So we have v squared over r, right? This is our centripetal acceleration. So if we have v squared, or we have v over r, which if you go back to the slide here, this is where we interpreted our angular velocity. We had delta theta over delta t, which we got from here. But now we have v over r, so we're going to talk about our r omega here. So since v squared, we're going to have r omega squared. Okay. So which still kind of makes sense as far as trying to interpret it from linear acceleration. Our velocity was squared in a linear acceleration, so it makes sense for our angular acceleration or centripetal acceleration to have our angular velocity squared. Okay, so for this example, the car following a circular path at a constant speed is accelerated perpendicular to its velocity as shown. So just because it's going around this curve here, if you were to complete the circle, you have a circular path. How would you find the magnitude of this centripetal acceleration? This curve has a radius of 50 meters, and the car is traveling at a speed of 25 meters per second, about 90 kilometers an hour. So after that, compare the acceleration with that due to gravity for this fairly gentle curve taken at highway speed. What is the acceleration in terms of gravity? Okay. So we have our velocity, right? Linear velocity, because this is meters per second, not radians per second. And we have our radius. It says curve of radius, right? So we can easily find our acceleration here. We have v squared over r. We have v here. That's 25 meters per second. Square that. Divided by our 500 meters. And that gives us a centripetal acceleration of 1.25 meters per second squared, right? So, but if we have to compare it as far as to gravity, all we would do is divide that by gravity. So the ratio between the two would be 0.128. So our relationship due to gravity is 0.28 g. Here we don't have meters, we have meters per second because we're still talking about our velocity here. If it was omega, if it was angular velocity, then yes, we would have gradients per second squared. All right, so that brings us all to centripetal force. So we're pretty much taking chapters 1 and 2, or 2, 3, and 4, and bringing that into our circular motion. So of course, a net external force is needed to cause any acceleration, just as Newton proposed in the second law of motion. So we're bringing in the laws that we learned in chapter 4 into chapter 6. So a net external force is needed to cause a centripetal acceleration. The centripetal force, signified by Fc, is the net force causing the uniform circular motion. We can define this force in terms of centripetal acceleration as F equals ma, basically, right? If you take away the c, you're still using F equals ma. So if we substitute everything that we know from from our acceleration, we get m r omega squared is our force here. All we're doing is substituting our a with v squared over r, which we just found out is this, right? So this is our new force for a circular path. Centripetal force is always perpendicular to velocity and causes uniform circular motion. So always perpendicular to our velocity here, right? Always tangent to it. The larger the FC, the smaller the radius of curvature r, and the sharper the curve. The second curve has the same b, but a larger FC produces a smaller r here. Okay, so this radius here is smaller, so we have a larger FC. Okay, so that brings us to example 6.4. This car on a level ground is moving away and turning to the left. The centripetal force causing the car to turn into a circular path is due to friction between the tires and the road. So now we're bringing in chapter 5. A minimum coefficient of friction is needed, or the car will move in a larger radius curve and leave the roadway. What is the coefficient of friction due to tires needed on the flat curve? Calculate the centripetal force exerted on a 900 kilogram car that negotiates a 500 meter radius curve at 25 meters a second. So 900 kilograms, that's our mass. 500 meters, that's our radius. 25 meters per second, that is our velocity. Assuming an unbanked curve, find the minimum static coefficient of friction between the tires and the road, static friction being the reason that keeps the car from slipping. All right. So here we have calculate the centripetal force of the 900 kilogram car, which negotiates the 500-meter radius curve at 25 meters per second. So here we are going to talk about our Fc equals mv squared. Oh, I wanted to point out the friction question that was on the PowerPoint. That's simply just looking back at the chart and looking up a coefficient of friction between our rubber and our dry concrete. So here for A, we have Fc equals mv squared. We have a mass, we have a velocity, and we have our radius. So all we have to do is plug in. So 900 kilograms times 25 meters per second squared over 500 meters, that gives us 1125 newtons. This is still in newtons, notice that, because we have still the same amount of units here in between. We have kilograms and then meters per second squared here. So for B, we are assuming an unbanked curve. Find the minimum static coefficient of friction between the tires and the road, static friction being the reason that keeps the car from slipping. So here, 6.12 is the actual figure for it. We know that we have to use our mu s times our normal force, where mu s is the static coefficient of friction. The normal force equals the car's weight, obviously, on the level of ground. So N is mg. Thus, our centripetal force here for friction is just mu s mg. And this is really just, the only reason they're saying for friction is because this is opposing the motion that the car is trying to go into, right? If the car is trying to slip, it's going to go away from our circular path. So we have to include centripetal force here. So we have mu s mg, right? So here, this equation here is just simply mv squared over r. So now since we know that, okay, we have Fc equals this, Fc also equals this, we're going to equal them to each other. So both our m's here cancel out, and we move over this g, so divide the g on both sides. So we are left with v squared over r times g. And after that, we can just simply substitute. 25 meters per second squared divided by 500 meters times 9.8. And our coefficient of friction is just 0.13. That's what it takes to keep the car from slipping. And this is what I meant. The friction is trying to keep the car in the same motion to make sure it doesn't slip. If it was kinetic coefficient of friction, might probably go the other way here, because that one would be moving in the other direction. Okay, misconception alert. The centripetal force is a real force that we can find and measure in physics. Some people often refer to centrifugal force, but it is important to note that this is not the real thing. This is a very common misconception. Think about a ball on a string. If you let it go or break the string while the ball is still following in a circle, the ball will continue to fly in a straight linear tangent to the circle. No net force acting on it means that it is following Newton's first law. What you feel when you travel in a circle that pushes you outward is just the inertia of your movement as it changes the direction. According to early accounts, Newton was inspired to make the connection between falling objects, falling bodies, and astronomical motions when he saw that the apple fall from the tree and realized that if the gravitational force could extend above the ground to a tree, it might also reach the sun. This inspiration of Newton's apple is a part of the worldwide folklore and may even be based in fact. Great importance is attached to it because Newton's universal law of gravitation, in his laws of motion, answered very old questions about nature and gave tremendous support to the notion of underlying simplicity and unity in nature. Scientists still expect underlying simplicity to emerge from their ongoing inquiries into nature. So that brings us to Newton's universal law of gravitation. The gravitational force is relatively simple. It is always attractive, and it depends only on the masses involved at the distance between them. Stated in modern language, Newton's universal law of gravitation states that every particle in the universe attracts every other particle with a force along a line joining them. The force is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. So, in layman's terms, Fg, gravitational force, is equal to big G, m1 and m2 are two units, are two particles that we're talking about, over our r squared, where G is just a constant, 6.673 times 10 to the negative 11th. But wait, you said that I know that Fg is mg on Earth, so what's the difference? Well, we can calculate the value of G with some clever application of Newton's universal law of gravitation. Basically, if you were to take the mass 1 of the Earth, mass 2 being an object, and the radius between the center of the Earth and the object, you would basically still get mg. First, we know that the gravitational attraction is along the line joining the center of mass of the two bodies. The magnitude of the force is the same on each, consistent with Newton's third law, and follows the relationship Fg equals G m1 m2 over r squared. We can assume that one body is the Earth and the other an object on the surface of the Earth. The distance between the centers of mass of the Earth and an object on its surface is very nearly the same as the radius of the Earth, because the Earth is so large, is so much larger than the object. So, where do we get our value of little g, which is just 9.8? But we also get, this other equation here. Well, for this figure, for A, we have Earth and Moon rotate approximately once a month and around their common center of mass. And for B, their center of mass orbits the Sun in an elliptical orbit, but the Earth's path around the Sun has some wiggles in it. Similar wiggles in the path of stars have been observed and are considered direct evidence of planets orbiting those stars. This is important because the planet's reflected light is often too dim for us to observe. Similar with tides. Ocean tides are one very observable result of the moon's gravity acting on the Earth. Because water easily flows on the Earth's surface, a high tide is created on the side of the Earth nearest to the moon, where the moon's gravitational pull is strongest. Why is there also a high tide on the opposite side of the Earth? The answer is the Earth is being pulled towards the moon more than the water on the far side, because Earth is closer to the moon. So, the water on the side of the Earth closest to the moon is pulled away from the Earth, and the Earth is pulled away from the water on the far side. As Earth rotates, a tidal bulge, an effect of tidal forces between orbiting natural satellite and primary planet that it orbits, keeps its orientation with the moon. So that's a lot of words. Basically, it's saying that the moon acts on the Earth. The water is really easy to move, so the moon's gravitation acting on the Earth. You can definitely see it on the waves, on the high and low tides. So even though, yes, we have high tides and low tides all across the Earth, the gravitation of the moon is really what's making that high tide and low tide. The sun also affects the tides, although it has about half the effect the moon does. However, the largest tides, called spring tides, A and B here, occur when the Earth, the moon, and the sun are aligned. The smallest tides, called neap tides, which is C, occur when the sun is at a 90-degree angle to the Earth-Moon alignment. Tides are not unique to Earth, but occur in many astronomical objects or systems. The most extreme tides occur when their gravitational force is the strongest and varies most rapidly, such as near black holes. A black hole is an object with such a strong gravity that not even light can escape it. This black hole was created by a supernova of one star in a two-star system. The tidal forces created by the black hole are so great that it tears matter from the companion star. This matter is compressed and heated as it is sucked into the black hole, creating a light and X-ray observable from the Earth. So, how fast must a satellite go in order to stay in orbit at 600 kilometers above the Earth's surface? I went ahead and wrote this one down here. So, if we're talking about an object on Earth, we are in a sphere, we're on a circular path. So we bring in our Fc for our force in a force centripetal force. So mv squared over r. But we're also talking about the Earth, right? And we just said that we can use this equation here, even though we're on Earth. So we have one force and we have another force, so we can go ahead and equal them to each other here. And as you can tell, we have an m1. I went ahead and just dictated this m1 just to keep it simple. We have m1 on both sides. They cancel out. We have an r here and an r squared here. Where to multiply just one r. Here they cancel out. So we're left with b equals gm squared over r, or m2 over r, I'm sorry. To get rid of a square, we square root. So this is our final equation here. So for here, we're saying that, okay, the object really doesn't matter here because the mass of the other is so great anyway. So we're going to take m2 to be the mass of the Earth, which is 5.98 times 10 to the 24th. We have our g, 6.67 times 10 to the negative 11th. And for our r here, even though we're trying to stay at 600 kilometers, we still have to incorporate the radius of the Earth. All right, so we have to add the two radiuses. So once we do all that, square root it, we are left with 7.903 times 10 to the third meters per second. That's how fast you have to be going to keep a satellite at 600 kilometers above the Earth's surface. Okay, so we all experience weightlessness. In contrast to this tremendous gravitational force near black holes is the apparent gravitational field experienced by astronauts orbiting Earth. Weightlessness doesn't mean that an astronaut is not being acted upon the gravitational force. There is no zero gravity in an astronaut's orbit. The term just means that the astronaut is in free fall, accelerating with the acceleration due to gravity and no other force acting on it. If an elevator cable breaks, the passengers inside will be in free fall and will experience weightlessness. We can experience short periods of weightlessness in some rides in amusement parks. Weightlessness just means that there is no force other than gravity acting on you. Especially, this means no normal force, which is, if you remember, is actually the force that the scale measures when you stand on it. So for astronauts, like I was saying at the beginning of this slide, they do experience the force of gravity all the way out there in space, but they're so far out there that they don't experience it as much as we do here on Earth. So the forces are still being acted on them, they're just not as great. Okay, so the Cavendish experiment. Cavendish used an apparatus like this to measure the gravitational attraction between the two suspended spheres, M, and the two on the stand, big M. By observing the amount of torsion, twisting, created in the fiber. Distance between the masses can be varied to check the dependence of the force on the distance. Modern experiments of this type continue to explore gravity. So it's just an example of the experiment. Okay, so that brings us to satellites and Kepler's laws. So now that we're in the aspect of space, we can go ahead and talk about some space laws. Examples of gravitational orbits abound. Hundreds of artificial satellites orbit Earth together with thousands of pieces of debris. The moon's orbit about Earth has intrigued humans from time immemorial. Orbits of planets, asteroids, meteors, and comets about the sun are no less interesting. If we look further, we see almost unimaginable numbers of stars, galaxies, and other celestial objects orbiting one another and interacting through gravity. All these motions are governed by gravitational force, and it is possible to describe them to various degrees of precision. Precise descriptions of complex systems must be made with large computers. However, we can describe an important class of orbits without the use of computers, and we shall find it instructive to study them. Okay, so these orbits have the following characteristics: a small mass m orbits a much larger m. So you could say like the moon and the Earth. This allows us to view the motion as if big M were stationary, in fact, as if from the inertial frame of reference placed on M, so as if we were saying that Earth is the big M, moon is the little m. Without significant error. Mass M is a satellite of big M, so just as the moon is a satellite of the Earth, if the orbit is gravitationally bound. The system is isolated from other masses. This allows us to neglect any small effects due to outside masses. So, just because we're talking about the Earth and the moon doesn't mean that the sun, doesn't mean that the other planets, uh, a comet coming by, that they're not acting on our Earth. We're just going to neglect them for now because we know that the Earth and the moon, just as an example for now, they're the closest to each other. The conditions are satisfied to good approximation by Earth's satellites, including the moon, by objects orbiting the sun, and by the satellites of other planets. Historically, planets were studied first, and there is a classical set of three laws called Kepler's laws of planetary motion that describe the orbits of all bodies satisfying the two previous conditions, not just planets in our system. Okay, so Kepler's first law is the orbit of each planet about the sun is an ellipse, with the sun at one focus. Kepler's second law is each planet moves so that an imaginary line drawn from the sun to the planet sweeps out equal areas in equal times. And the third law is the ratio of the squares of the periods of any two planets about the sun is equal to the ratio of the cubes of an average distance from the sun. Basically, this is T1 squared over T2 squared is equal to R1 cubed over R2 cubed. So this one is pretty much saying, I want to talk about the second law real quick. That one's saying that even though, yes, we do move in a circular orbit, circular path, we are saying that the center of the Earth and the center of the moon is the radius we are going to take, not, our poles, not a specific distance, the center to center. That's our imaginary line. Same thing can be said if you're talking about any other body, whether it's the sun and the Earth, the sun and Neptune, any of that stuff. Okay. For A, here, an ellipse is a closed curve such that the sum of the distances from a point on the curve to the two foci, F1 and F2, is a constant. You can draw an ellipse as shown by putting a pin at each focus here. 1 and 2. And then placing a string around the pencil and the pins and tracing a line on paper. So pretend that this is a string here. It would go on an ellipse. A circle is a special case of an ellipse in which the two foci coincide. Thus, any point on the circle is the same distance from the center. So this would be more like the path the Earth takes around the sun. For any closed gravitational orbit, little m follows an elliptical path with big M at one focus. So, like I said, sun, and we're just going to say any planet here. Kepler's first law states this fact for the planets orbiting each sun. The shaded regions have equal masses, equal areas, I mean. It takes equal times for M to go from A to B, and from C to D, and from E to F. The mass M, small m, in this case the planet, moves fastest when it is closest to big M, in this case the sun. Kepler's second law was originally devised for planets orbiting the sun, but it works beyond just this simple example. So as you can see here, this planet here, this little m, is going, and it moves the fastest while it's closest to the sun. That's why it covers more area here. Now, the farther it is, the longer it takes to cover that same area. Okay, so example 6.7, we're going to talk about Kepler's third law. The ratio of the squares of the periods of any two planets about the sun is equal to the ratio of the cubes of their average distances from the sun. In this equation, which is the equation T1 squared over T2 squared equals R1 cubed over R2 cubed. Using this law, and given that the moon orbits Earth each 27.3 days, that is an average distance of 3.84 times 10 to the 8th meters from the center of the Earth, calculate the period of an artificial satellite orbiting at an average altitude of 1,500 kilometers above the Earth's surface. 6.7. Here we go. All right. So we are obviously going to use this equation here. We are asked to find T2. The given information tells us that the orbital radius is 3.84 times 10 to the 8 meters, and that the period of the moon is T1, 27.3 days. The height of the artificial satellite above the Earth's surface is given, so we must add the radius of the Earth, which is 6380 kilometers, to get R2, which is the addition between the two, which is 7880 kilometers. Now all the quantities are known, so we simply rearrange this equation here to solve for T2. So you can do this one of two ways. You can multiply the T2 to the right and then multiply and divide the R1 and R2 to the left. Or you can simply do an inverse, which means flip everything at the bottom to the top and everything at the top to the bottom, and then divide the T1. Either way, you will end up with this equation here. Obviously, to get rid of a square, you square root it. But in this case, you have to do the exponent here of a square root, which is just 1/2. So if you do 1/2 times 3, you get 3 out of 2. Don't forget here to change your T2 into days here, or from days to hours, I mean. And we end up getting 1.93 hours. That's how long it takes for the satellite to revolve. Okay. Our last slide shows that the universal law of gravitation is a good example of a physical principle that is very broadly applicable. That single equation from the gravitational force describes all situations in which gravity acts. It gives a cause for a vast number of effects, such as the orbits of the planets and moons in the solar system. It epitomizes the underlying unity and simplicity of physics. Physicists love universal laws because they are very simple to describe most, if not all, interactions of all type. One of the most active research avenues in physics today is the search of a grand unified theory that will allow us to unite the gravitational, electromagnetic, weak and strong forces into different manifestations of just one single force, which we hope. So this is the end of this chapter. From this chapter, I would definitely focus on the gravitational portion. The circular motion we will talk about again, I believe in chapter 10 or 11. So we will review that again. But this is the only section of the semester where we talk about gravitation.